everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the Boeing 737 Powerplant. So the presentation is going to cover the engines and displays on all models of the 737, from the original through to the MAX. My usual disclaimer, please always treat your company training and their manuals as the authoritative source of information. So, contents for this presentation, quite a lot to fit in here. We got all the various engine types, components, upgrades and hush kits, oil, fuel, PMC and EEC, ignition and starting, displays, vibration, reverse thrust, engine ratings, bite testing and limitations. Alright, so here's an overview of the four engine types used on each generation of the 737. For the originals it was the JT8, classics onwards it was the CFM56, the Dash 3 on the classics, Dash 7 on the NG and the Leap 1B on the MAX. The engine diameters, as you can see, they've all increased over the generations, thereby improving the bypass ratio. Fan blades, I know the original didn't have fan blades referred to as fan blades, the first stage compressor, but for the sake of argument let's call them fan blades here. Those numbers unusually went up for the classics and then started coming back down with the MAX. Made of titanium except in the MAX when it was carbon fibre. But the significant thing I think really is the thrust. It started off at 14,000 on the original Dash 7 JT8, and over the lifetime of the 737 it's more than doubled to 29,317 pounds of thrust. That's on the highest model of the Leap 1B. Alright, nothing particularly technical here to say, it's just a sort of pleasing collection of photos of those fans. Originals up there in the top left, classics NG, and then the fairly distinctive Leap 1B on the MAX. So while we're talking about fans, let's take the opportunity to mention the spinner shape at the centre of the fan. The original CFM56 spinner for its first few years was conical, very sharp pointed, quite a ferocious looking thing actually, and it was shaped like that to minimise the amount of ice that would form on the spinner. Unfortunately that shape allowed any precipitation, most notably hail, to pass straight into the core of the engine, which in the early days of the CFM56 used to lead to flameouts. So the shape was changed to this sort of elliptical, round nose, sort of bulbous spinner. But as you can see from the photo I've used here, whilst it did deflect any precipitation away from the core, the large frontal area meant that more ice was picked up in the first place. So the CFM56-3 stuck with that shape of spinner up until the Dash 7 on the NGs, and they hybridized the two shapes, the conical and the elliptical, to make a conliptical profile. So it's got a conical front and an elliptical base, and that solves both problems. So you don't get the ice accretion on it, and the base bounces the precipitation away from the core. Clever stuff. Alright, so let's go back and look at each engine in a little more detail. The JT8 was the original choice of Powerplant. Originally penciled in as the JT8-1, but before the first order had come in, Boeing had upped it to the Dash 7, and this was for commonality with the 727. Although it had the same thrust as the Dash 1, it's flat rated to give the same thrust at higher ambient temperatures, and this became the standard power plant for the 100, and they increased in odd number increments, so it went 7, 9, 11, 13, 15, right the way up to 17, which had 17,400 pounds of thrust. The very first JT8s had auxiliary inlet doors, which I've indicated there, and these are just spring-loaded things, so that there's no big mechanical mystery going on in here. It's just spring-loaded doors, and whenever the engine was sucking, maximum amount of air, bigger pressure differential, then these auxiliary doors would open to give additional engine air, and they would naturally close again as the airspeed increased, causing the inlet static pressure to rise. They didn't last very long. I think they were gone by the Dash 9. Anyway, moving on to the classics and the CFM 56. I'd say the sole power plant for all 737s after the 200. The core of this is produced by General Electric, and I'm told it's identical to the F101 engine used in the Rockwell B1. Snecma produced basically everything else other than the core. The fan, the intermediate compressor, LP turbine, thrust reversers, and all the accessories. So the name CFM is actually a hybrid of the two manufacturers' engine designators. General Electric call their engines CF, and Snecma call them M for motors. So the name CFM came about. This is just a video I took of the engine windmilling in the air on a walk around on a windy day. The core engine, it's governed by metering fuel, but the fan is a free turbine. The advantages of this include minimised interstage bleeding, fewer stalls or surges, and an increased compression ratio without decreasing efficiency. One problem with such a high bypass engine was its physical size and ground clearance, and as we know, particularly if you've seen my presentations on the Max and MCAS, this really came to the fore in the Max version. But anyway, it was still an issue right back in the days of the classics. So the large bypass engine was fitted by putting the accessories on the lower sides, but not the bottom, where ground clearance will be compromised. So they're actually put to the left and right hand sides as you look at it in this picture. That flattening of it kind of gives the intake lip the so-called hamster pouch look. The engines were moved forward and raised level with the upper surface of the wing and tilted 5 degrees up. Again, this is something which will sound familiar to those who've studied the Max. This not only helps ground clearance, but also directs the engine exhaust downwards, reduce some of the effects of pylon heating, and gives some vectored thrust to assist takeoff performance. The CFM 56-3 proved to be almost 20% more efficient than the JT8, so it was a huge step forward. Alright, so let's have a look at some of the basic components of the CFM 56. This particular photo is one I took of a Dash 3 on a Classic, but to be honest, they're virtually the same on the Dash 7 and pretty similar for the Leap as well. This is just the best picture I had, so I'm using this one. So the first item you see marked in the red circle there, they're the thrust reverse cascade vanes. They're just lifted here for maintenance. Normally they don't move. I'll come on to those in a bit more detail later on. But they wrap around pretty much the whole circumference of the engine, bar a little bit at the top where the hinging is, and a bit at the bottom where the bracket is. Up there, that's that little silver duct there. That's for the engine anti-ice, the anti-ice cowling with the yellow cap at the end, just for maintenance. You've got a pair of ignition exciters there for left and right ignition. Next unit down, that's the PMC. the brains of the engine, and the big tank down there is the oil reservoir. On the other side, and this is a 56-7, that unit there is the starter, and the large length of silver ducting, quite broad silver ducting from it, is the pneumatic manifold to the air starter. Notice that it's actually separate from the engine anti-ice manifold, which you can just see. I haven't marked it on this photo, but you remember it from the previous one. Over there in the 11 o'clock position of the engine. So on to the CFM 56-7. The diameter of the fan, 61 inches, I've said, so it's a couple of inches increase over the 5. A solid titanium wide chord fan. The engine's also got new low pressure turbine turbo machinery FADEC, a new single crystal material in the HP turbine. All of this gives an 8% fuel reduction and I'm told a 15% maintenance cost reduction, due in part to greater EGT margins compared to the 56-3. So again, huge improvement. One of the early options on the 56-7s for the NGs were dual annular combustors, and the designator for these engines was the 7B/2. These considerably reduce nitrous dioxide emissions, and they do this by getting a more complete combustion. So the engines they've got 20 double tip fuel nozzles instead of the regular 20 single tip fuel nozzles that the regular engine has, and dual annular shaped combustion chamber. The number of nozzles in use actually varies depending upon the thrust required, whether it's just the basic 20 and then or the full 20-20 nozzles, or even there's actually a halfway stage as well called 20-10. This depends on the thrust required. So 20-20 mode is high power, as you'd perhaps expect for the most complete combustions. That's cruise M1 and above. So it's takeoff and climb. 20-10 mode's medium power, and 20-0 mode is idle thrust basically. So the leaner fuel air mixture reduces flame temperatures and gives higher throughput velocities, which reduce the sort of residence time available to form the nitrogen dioxide, or nitrogen oxide, sorry. Net result is up to 40% less NOx emissions than the standard engine. Personally, I've only flown these a few times on when I was testing 600 versions. And you could actually feel a little bit of vibration just on that transition between the different modes. It was a known issue, and it was notified, but it was just one of those things that you learn to live with when you flew the DAC aircraft. I don't know if any other models or airlines ever took up the DAC option, but certainly SAS had their entire fleet of 600s were DACs, which is where I took this screenshot from. Other upgrades to the CFM 56, and there have been several, but the big upgrades are the following. So on the classics, the 56-3 had a core upgrade in 2002. The HP turbine was redesigned and got a new nozzle, blade and shroud materials. That gave an EGT margin increase of 15 degrees and the fuel burn was reduced by 1%. Again, remember, EGT margins are very good for maintenance and longevity of the engine, and engine reliability is what that translates to, back to us as the pilot in the front, I guess. The next big upgrade was the tech insertion for the 7Bs. This was delivered as standard from June 2007, and that package included improvements to the HP compressor, combustor, and HP and LP turbines. Further reduced EGT margins by up to 20 degrees depending which version it was fitted to. Fuel burn dropped again by another 1%, maintenance cost by 5%, and NOx emissions dropped by 15 to 20%. So this TI basically made DAX kind of redundant. It did everything that DAX did, only better. TI engines have got the /3 suffix on the designation, which you may see in the tech log, or on the Medlink engine config page. The /3 is shown there. There is a further version with an optional F rating, which has got a 20 degree higher redline EGT, but the DU and the FCON limits are actually unchanged, so it's a sort of behind the scenes improvement on redline EGT. And the last big upgrade to the 7s was the 7B Evolution. This came in mid 2011. Gave another 1% fuel saving over the regular 7B, and the easy way to identify this, because you can identify externally, is by looking at the back of the engine there. So the nozzle is 18 inches shorter. The plug's actually also short. It's 2.5 inches shorter, but I think it's a bit of an optical illusion. It actually looks longer even though it's shorter because the nozzle is so much shorter. Because of the nozzle and the plug being shorter, the heat shield above the engine there has got new titanium pans and inboard plume suppressors and side scoops, all to cope with these higher temperatures from the short exhaust. You can intermix the 7BEs with the other versions, subject to updating the FMC model engine database and the EC softwares. And then the biggest and best improvement of them all to the CFM56, and it is still a CFM56. It just goes by the name LEAP. Was the LEAP engine. LEAP standing for Leading Edge Aviation Propulsion. 69.4 inches diameter on the 737, a little bit bigger in diameter on the Airbus. 18 woven carbon fibre fan blades. Gives it a bypass ratio of around about 9 to 1 versus 5 to 1 to the 56-7. And the largest version so far, and I don't know if they're planning to do a bigger version for the Max 10, but so far the largest version is 29,317 pounds thrust. The turbine has got flexible blades, which is new. These are manufactured by a resin transfer molding process, and they're actually designed to untwist as the rotational speed increases. There are new hot section materials as well, and this delivers an overall pressure ratio of 41 to 1, which is significantly more than the 28 to 1 of the CFM 56-7s, and 15% more fuel efficient, which is what we see in the flight deck, as it seems to sip fuel on the fuel flow gauges. External differences, there are several. Redesigned engine nacelle, laminar flow lips, new struts and fairings. Thrust reversers were redesigned, and revised efflux pattern, and revised chine size and position, which you can't actually see on this photo. And these were all for aerodynamic fitting. The most noticeable thing we see at the back are the chevron patterns or sawtooth patterns on the trailing edges of the fan nozzles, developed by NASA apparently to smooth the mixing of the fan and core airflows. That reduces the turbulence between the sort of shear layer between the two speed of airflows, and that gives a significant reduction in noise. So talking of noise, perhaps one of the most significant improvements in the power plants over the years has been to the noise levels. On the graphic at the bottom there, you can see the red footprint. These are takeoff noise footprints. Is for the original 200 series. The 75 decibel level stretched 12 miles along the takeoff flight path. I mean, those of us old enough to remember hearing these things take off, I mean, crikey, you couldn't miss them. Almost a conversation stopper. The yellow graphic is for the NG, and the green is for the Max. So you know, it's a good sort of visual indication of how much the noise has reduced over the years, which is a good thing, of course. So noise reduction's been in place on the 737 for many decades. The first hush kits were, you couldn't see them. Well, not unless you've done like me and looked straight down the back of the exhaust. These are exhaust mixers, and these work in exactly the same way as that fairing on the Max's LEAP engine, where it's designed to again mix the airflows, mix the two speed of the airflows, and the better that mixing is, then the quieter and actually the more efficient the engine. So those were new. They're I say fitted behind the LP turbine. They mix there is. I mean, you perhaps be surprised to hear, but there is actually some bypassed air on a JT8. Not very much, but this mixes that bypassed air with the core air. Noise reduction from this about 3.6 decibels. What else have we got there? Yeah, now these are the more obvious hush kits. These are the visible ones. These started appearing in the early 90s. This particular one was from Nordam, but Avero did them as well. The EU actually apparently tried to ban all hush-kitted aircraft flying into the EU in 2002 because they use more fuel. Well, fortunately, there was strong opposition to this, and the EU relaxed and did allow hush-kitted aircraft to use any airport which would accept them. These are actually, as the decal on the side of the engine shows, these actually just about, but nevertheless they do meet FAA Stage 3, which is known in the EU as the RSET Chapter 3. So they were actually compliant, and unfortunately not banned from the skies of the EU. The CFM56 also had its own hush kitting, a little less notable than that previous JT8 one. The photo here is of the turbine exhaust area, so a similar photo to the one I took of the JT8 before. No mixing is required because the bypass air is exhausted coaxially. But the engine can be fitted, and most of them have been fitted, with hardwall forward acoustic panels, and they absorb the noise at the nacelle by 1 decibel. The Classic family is already Chapter 3 noise certified, but in 2012 it actually got an AFM option to make it Chapter 4 noise compliant. The NG and the Max are both straight out of the factory Chapter 4. So reliability. This is one of the huge positives about the CFM56. It is incredibly reliable. Now these stats, and the most recent I could find, and they're 15 years old, issued in July 2006, but I don't believe they will have deteriorated any. In fact, I'm quite sure they have improved. But back in 2006 they were flying about 100,000 hours a day, amassed 325 million flight hours. They were averaging 18,000 hours before first shop visit, before first overhaul. And one engine in particular, this is late data that I managed to get from somewhere. In 2012, one engine actually achieved 50,000 hours on the wing without a shop visit. The engine shutdown rate, so this is probably the bit that appeals to us as pilots, is, well, again, this is 2006 data. It was 1 in every third of a million flight hours. So if you were to do your 900 hours a year, you get one shutdown every 185 years. So statistically, it isn't going to happen to you. Even though we practice this ad nauseum in the sim every 6 months, but there we go, that's another story. Oil. That's the oil tank on the 56-7, and the oil indications you'll see above, or some of them. Oil pressure is measured before the bearing, so it's measured where you need it. So that's why it's measured there. The most sensible place to measure it. Oil temperature is also measured at the most sensible place, which is on return, which is where it's at its hottest. And the oil quantity is measured in the tank, and that drops after the engine starts. So you will see a drop in oil quantity after engine start. That's normal, don't worry about it. Oil pressure is unregulated. So the yellow band, your 13 to 26 psi band, it's only valid at takeoff thrust. But the lower red line, the 13 psi, that's valid at all times. If the oil pressure is ever at or below the red line, the low oil pressure light will illuminate, and you should consider shutting that engine down. It doesn't say must shut it down. It very much depends what else is going on, but certainly worth considering. There are two fan inlet temperature sensors in the CFM 56-3 intake. One at the 2 o'clock, that's used by the PMC, and the one at 11 o'clock is used by the MEC. The MEC uses the signal to establish parameters to control the low and high idle power schedules. The CFM 56, the dash 7 on the NG, that's just got one fan inlet temperature probe, which is for the EEC. Temperature data is used for thrust management, variable bleed valves, variable stator vanes, high and low pressure turbine clearance control system. So it's used for a whole load of stuff. One slight difference between the NG and the classic temperature probes is that the NGs only use the inlet temperature data on the ground and for 5 minutes after takeoff. Thereafter, they use temperature data from the ADI-RUs. So we've mentioned the MEC and the PMC. This is for the originals and the classics. So that's what they look like in the images on the right there. On the originals, fuel flow, which is thrust, primarily controlled by the hydromechanical MEC in response to thrust lever movement. The classics, that had a further stage of refinement by adding on a PMC. So there was no PMC on the originals, that came in on the classics, and that acts, as you probably know, without thrust lever movement. For the NGs and the MAX, the MEC was replaced by an HMU, and the PMC was replaced by the EEC. They do very similar things, but slightly different, hence the different nomenclature. I'll come on to those in a moment. The classics may be flown with the PMCs in op, but an RTOW penalty is imposed because the M1s will increase by around about 4% during the takeoff roll due to the windmilling effects of that increase in airspeed. There was a Flight Ops technical bulletin about this issued in '85. The reduction in RTOW avoids reaching any engine limits. You can either reduce the takeoff weight or the M1, but the way they went about it was to reduce the takeoff weight. But it amounts to the same thing. The thrust lever shouldn't be readjusted during the takeoff after the thrust is set because of this windmilling effect, unless a red line limit is likely to be exceeded. So let the M1s windmill up to the higher M1 it's all catered for by that reduction in by the RTOW penalty. So on the NGs, we've got the EEC, the electronic engine control. Each engine, so that there's one of these on each engine, it's got its own full authority digital EEC known as a FADEC to control M1 with fuel flow. The EEC also regulates the maximum M1 for the ambient conditions and the bleed air demands as well, so it takes all of that into consideration. The EC provides M1 and N2 redline overspeed protection in both normal and alternate modes, but it doesn't, oddly enough, provide EGT redline exceedance protection except during a ground start. So there we go. Keep monitoring the EGTs because the EC won't do it for you. The EEC modes, there are in fact 3 of them, and these are shown on the aft overhead panel on the engine and reverse panel there. And this is showing normal mode, which is the mode we normally see it in. So for this, the EC uses sensed flight conditions and bleed air demand to calculate the M1 thrust settings. So that's ops normal. The soft alternate mode. So if the main channel of the EEC fails, it'll switch into the other channel, and this is alternate mode. Now, when it does this, it uses the last valid flight conditions to define the engine parameters, which allow the mode to occur with no intermediate change in immediate change in engine thrust. In other words, it's a kind of seamless flow. Or bridge between normal mode and alternate mode is this soft alternate. It's an intermediate stage. Any thrust rating shortfalls or exceedances may occur as the flight conditions change because it's using the last known parameters. So what you need to do is you need to get out of this soft alternate mode and get yourself into hard alternate. And you do that by bringing the thrust lever back to idle or by manually pressing that alternate button. Hard alternate, so on this the EC reverts to alternate mode thrust schedule, and the hard alternate mode thrust is always equal to or greater than normal mode thrust for the same lever position, but it's all taken care of, and it's quite acceptable to fly in alternate mode. The HMU, hydromechanical unit, is what replaced the MEC on the Classics, does a very similar job, sends metered fuel to the engine as commanded by the EC, also takes commands from the start levers and the fire handles to control the high pressure shut-off valves to shut down the engines. The EC also controls various airflow and clearance control systems using HMU servo fuel pressure. So if we stop and think about that for a moment, using HMU servo fuel pressure, it actually uses fuel to push and open and move the various vanes and valves, which is an interesting use of fuel, but that's what it does, and you can see the list of things that are done there. Alright, a word about idle. There are many different idles, and the EEC will automatically select ground idle, flight idle and approach idle, or the minimum. It'll set the minimum idle M1s for those phases of flight. Approach idle is higher than flight idle, and that kicks in when the flaps are in landing configuration, and this is to give a better spool up time to go around thrust. The certification limit is 8 seconds from idle to full thrust, but basically the sooner you get go around thrust after you've asked for it, the better. If you think of your worst case scenario, to go around from minimums when you've got terrain ahead of you and you need your minimum 2.5% go around thrust on one engine, that's what this is all based on, and why we have an approach idle which is higher than flight idle. In flight, if a fault prevents the EC from receiving flap or anti-ice signals, approach idle will automatically begin below 15,000 feet. And ground idles selected both after start and also 5 seconds after touchdown, and it's lower than flight idle. The two pictures I've got shown up on the right there, the top one is the regular ground idle that you'll be used to, just a shade under 20% M1. The bottom of the two pictures, now you can see from the TAT that this photo was taken on the ground. Obviously that wasn't a true OAT, that's just the TAT probe going a bit berserk, as it often does on the ground. But you'll notice that those idles are really high, and this was an aircraft fitted with a high altitude landing system, and that was a modification. One of the many mods to the HAL system was this higher ground idle speed. Okay, ignition. There are two independent AC as opposed to DC, but AC ignition systems, left and right. We know this because the switches are there for us in the flight deck. The exciters, which are these boxes here in the top picture, these convert your 115 volts AC from the EC to 15 to 20,000 volt DC and send it off to the spark igniters. So in the picture, the cables coming in from the right, the thinner ones, they're your 115 volts AC coming from the EC, and the thicker cables on the left, they're the ones going off to the spark igniters. The power source for these, the multiple levels of redundancy here. The feed for left ignition is transfer bus 1 for engine bus 1 and transfer bus 2 for engine 2. The feed for right ignition is always the AC standby bus, which is why it's best to do your first start of the day on the right igniter. Then you know that the AC standby bus is working, so that if anything were to happen in flight, and you were to lose both engine jennies, then you know that you've got a power source. If you recall from the electrics module, from the batteries will feed the AC standby bus, and you can get a spark for the engines. Always useful. The off position on the switches, this is the normal in-flight position, because normally in flight no igniters are in use, because the combustion's self-sustaining. Ground and flight positions use the selected igniter, and flight uses both igniters. Note that the EC will automatically use both igniters if it detects a possible flame out, and there are various parameters and conditions for that. Also for in-flight engine starts, the ground position, it will arm both igniters. On the originals, these are two panels. Obviously you can see the bottom panel is one that I mocked up just for this presentation, but the top one's a genuine photo. So instead of continuous, they had low ignition. And as you can see from the bottom graphic, on some aircraft that there was a low and a low ignition, a low left and a low right ignition. For many years, the QRH used to use the word on for ignition. For instance, in the one engine in uplanding checklist to cover the various options for mixed fleets. So rather than say low ignition or left ignition or right ignition or even cont when the classics came in, it just said on, which was a lot easier. There's no left or right selector on the originals, but there are still two independent ignition systems. For the NG, there is an automatic ignition option. I haven't seen many aircraft with this fitted. It's quite a rare or a low uptake on this option, but if you had it, then it would just put the ignition on whenever flap or engine anti-ice is used. All NGs will allow the EC to put the ignition on or off under the following conditions. So it'll put it on if a flame out is detected, and it will switch it off if there's a hot or wet start detected. Starting. So the minimum duct pressure for start, this is on the classics, 30 psi minus half psi per 1,000 feet pressure altitude, and a max 48 psi. There's a minimum 25% N2 or 20% N2 max motoring to introduce the fuel. Any sooner than that and you could find yourself having a hot start. Max motoring defined as when the N2 doesn't increase by more than 1% in 5 seconds. The aborted engine start criteria: no M1 before the start lever is raised to idle, no oil pressure by the time the engine is stable, no EGT within 10 seconds of the start lever being raised, and no increase or a very slow increase in M1 or N2 after the EGT indication. And for the classics, EGT rapidly approaching or exceeding 725C. Note that an abnormal start advisory doesn't by itself mean that you have to abort the engine start. And I've had plenty of occasions when I've had the abnormal start advisory, but the engine's gone on to start quite normally. The starter cutouts, approximately 46% N2 on the classics, 56% on the NG and the Max. The duty cycle limit, for the originals and classics it was 2 minutes on, 20 seconds off. For the first attempts, second and subsequent attempts, 2 minutes on, 3 minutes off. For the NG, it's 2 minutes on, followed by 10 seconds off. And for the Max, they've increased that to 3 minutes on, followed by 10 seconds off, because the leap takes so long to start. Alright, a word about in-flight starts. This was a photo that I took during an air test of a crossbleed start. As you know, there are two types of in-flight starts: crossbleeds or windmills. The aircraft will, or the NG will let you know which is which, or if you, I should say, if you have to do a crossbleed start, the red arrow there is pointing to the little crossbleed caption above the N2 gauge. And obviously this is based on altitude, airspeed and N2, and it's as per the relight envelope in the QRH. I say this photo was one I did on air test, and where I was doing the crossbleed at the worst case conditions, and you can just about see on the standby altimeter and an ASI, just a shade under 20,000 feet at 140 knots, which is the extreme sort of top left corner of the envelope, i.e. the highest and the slowest, the worst case scenario for a relight. And I must have done, I don't know, many hundreds of in-flight engine relights, and they all worked absolutely fine, which is comforting to know, I think. The other kind of start is the windmill relight. Again, this was taken in flight on test. So if you got speed above 275 and you're below flight level 270 with more than 11% N2, and these figures, by the way, they vary slightly for DAX to SAC aircraft and different engine modifications. So check the relight envelope in your QRH. But this particular one was for a windmill relight. Now the EGT start red line limit, it can be shown depending on the start logic as determined by the EC. If there's only one EGT shown, this is the in-flight start EGT limit. If both red line and the start red lines are shown, then that start limit red line is the in-flight start EGT limit for all engine starts, and you can see it on this photo here. So quite a rare case of a gauge having two red lines or upper red lines. And again, I say I did hundreds of these, and they all started absolutely fine for me at the extreme high altitude and low speed, a minimum N2 allowable. Here you can see I'm at 29,000 feet, so I've got about 1,500 feet further to descend, and I've got about 3% N2 in hand before relighting there. On the Max, it's a whole different kettle of fish with the Leap 1Bs. It takes, as I've already mentioned, a lot longer. It takes about 3 minutes to start a Leap engine. After the big thing is the bowed rotor motoring. That's why it takes so long. When the start switch is moved to ground, the EC starts performing this bowed rotor motoring, which you can see the enunciation motoring on there. And this is to straighten the N2 shaft, which may have bowed. I sort of bent or dipped due to the difference in heat between the upper and lower parts of that N2 rotor from the previous shutdown. Most of the bow occurs during the first 45 minutes of shutdown, but it can remain for up to 7 hours. So you'll find that the length of time that the EC wants to motor the engine for is inversely proportional to the turnaround time. So if you're doing a quick turn on a hot engine, then the motoring will be quite high, or last quite a long time. Last anywhere from between 6 to 90 seconds at an N2 of between 18 and 24%. So the actual motoring time and N2s will be determined by the ECs. At 25% N2 or max motoring, when you move the start lever to idle, the EC then performs a test of the TCMA, the thrust control malfunction accommodation, and the electronic overspeed system functions. So what you see as the part of the fuel flow indicating 0, the engine fuel shut-off valve opening and closing repeatedly, and the engine valve close light illuminating bright blue until the test is finished. And then the start sequence continues. All right, so let's take it right back to the 200s and have a look at some round dial instruments. Now, with the exception of the top gauges, which are the EPA gauges, these are just the same instruments that you see on the Max. They're just displayed differently. You've got all the same instruments there that are on the Max. The blanking plate down at the bottom right, that's where the vibration gauges were, and the placard on that blanking plate is just for EGT limits, although they are actually marked on the gauge as well. All round dial aircraft had an oil quantity test button. Some were, I mean, these were in various locations, but they were up near the yaw damper indicator. And you have to press that on your pre-flights and see that the oil quantity gauges wound down to 0 when you pressed it, and then you could release it. If not, then tell an engineer and he'd rectify that before you could fly. These are the other sort of more modern, if modern is the word to use, more up-to-date round dial instruments, and these were fitted to both the originals and the early classics. These have got LEDs for a digital readout on top of the analog display, and also red warning lights for exceedances on the M1, N2 and EGTs. And because these were fits to both originals and classics, the only way you can really tell which one you're in is to look for an EPA gauge. This one doesn't have an EPA gauge, so we know that this is actually a classic. After a few years, in 1988, the EIS system came in, which was ergonomically much better. And much more reliable as well. Electromechanical instruments, whilst we love them and they're all very nostalgically wonderful, they do have a habit of sticking or breaking. Digital electric instruments are by and large much more reliable. Not only that, £10 lighter in weight, reduced power consumption, and perhaps another, hugely important feature of these. They're not just digital for digital's sake. There are actually little computers back there, and hence was born the concept of byte testing, built-in test equipment. So these can actually store exceedances and give you a limited amount of diagnostic information, which the round dial instruments never could. So this is a photo of me doing a byte test on the EIS display. The photo is actually of me doing it on the primary EIS display, but it was also available to be done on the secondary one as well. There's a very tiny little recessed button which you can see that the tip of my biro is just pushing in at the moment whilst the test is being conducted. You can only do this when the engines are below M1s are below 10%, i.e. you're on the ground. You press and hold the button and it shows this LED check, during which various checks are conducted, and if any of the checks fail, it'll actually write the appropriate code in the place of the effective parameters readout. Now the code here you can look up on the table is ERF, which is actually the most common one, and that just means that the exceedance RAM is full. So it's basically saying there's been so many exceedances which haven't been cleared from my memory. So there you go, bad engineers. If you press the button twice, then it will actually show you what those exceedances are. On the NG, the displays are all completely different. Same instruments, but different way of presenting the information. And this is the upper DU, and this is the normal display. All it shows is M1, EGT, and the fuel quantity. And as I've written there, this decluttered or sparse, depending on your point of view, display can take some getting used to after the earlier series. Yeah, they really kept a lot of information in the background on the NG series onwards. I mean, it's all there to be seen if you want to see it, but they decided that less to look at was easier to monitor, I guess. If a system's displayed on the lower DU after it pops up with an anomaly, then the upper DU changes to compact mode, and compact mode looks like that. Sorry about the blurred photo. It can also be shown when the MFD engine button is pushed for the first time after the aircraft's been completely shut down. So this photo shows the display after one engine's been started. So you can see that there are some blank parameters on the number one engine. So they're the ones controlled by the EC, which isn't yet powered until the start switch is switched to ground. So that's an easy way of knowing which are the EC control parameters. I say when the associated start switch is selected to ground, sometimes they might appear later, and that would be at 15% N2. That's if the aircraft's got no AC power on it. And that is because the ECs, as I mentioned on an earlier slide, what the power source for the EC was, but there's actually another power source, which is that they've got their own alternators. So if all else fails, the ECs will power themselves from an alternator off their respective engine. So that alternator only gets up to speed at 15% N2, which is why the parameters may come in on there. During startup, the ECs receive electrical power from the AC transfer buses. Their normal source of power, as I said, their own alternators, and they kick in at 15%. The lower DU looks like this. Normally only displayed on the ground during engine start, but you can bring it up at any time by pressing the engine button. When an anomaly is detected, it will pop up automatically. For the Max, the displays are really very, very similar to the NG. Just a few more things on there, like flaps and fuel, just to squeeze into the one display. So normally there's just the M1 EGT and fuel flow displayed. But again, if you press the MFD engine button, the other parameters come into view, giving that you've now got a sort of pseudo compact mode look where everything's on display. For the Max, there are two new crew alerts, and these are thrust and fuel flow. In simple terms, thrust will illuminate if the actual thrust is more or less than the commanded thrust, and fuel flow will illuminate if the actual fuel flow is abnormally high compared to the FMC expected fuel flow. Note the entire block will blink for 10 seconds, then stay steady amber for as long as that condition exists. Thrust mode annunciations, there are a huge number of them. Depending on the fit on your aircraft, you may see some of these. You're probably unlikely to see all of them. They depend on the type of takeoff, the climb, phase of flight, and customer selectable options. Things like D-rates and quiet climbs are notable options. Most of them refer to assumed temperature thrust reduction, D-rate or bump takeoffs, but the full list is there. A quick word on colour coding. For the NG and the Max, the red line is the maximum limits. The amber arc, which you can barely see, but it's just there, is the cautionary range, and the white arc is the normal operating range. For originals and classics, it's as it was, except that the normal operating range is a green arc rather than a white arc. Airborne vibration monitoring. Okay, all series of the 737 have got a facility for AVM, but not all of the originals actually had them fitted. And you recall an earlier photo showed the engine instruments of an original that actually didn't have vibration gauges. Most of them do, though. In fact, the early 737-1 and 200s had quite an elaborate vibration system, and you can see from this photo here, you could actually select where you were measuring vibration from, either the turbine or the inlet. Some aircraft even had a high and low frequency filter selection switch, but I think they were fairly thin on the ground. The displays, they've changed over the years, but they're essentially the same. It's always been a number between 0 and 5. There's an optional vibration caption for classics, which I've shown there. I didn't see very many of these. Some airlines had them, but not many at all. And the QRH procedure for high vibration, that kicks in at 4 units. So a word about these units. Now, I've got a quote here from the UK AIB, Air Accident Investigation Branch, from an investigation they did on a 737-400 belonging to British Midland, which had an accident at Kegworth. And they did a lot of analysis of the vibration gauges, and from that they said that the vibration units are non-dimensional, and the figure of 5 units represents a level at which vibration should be apparent through the airframe, but of itself should not jeopardize the integrity of the engine. So good to know. And again, following the Kegworth accident, and a couple of other let's say premature shutdowns, Boeing issued this flight ops review across all fleets, actually, not specifically the 737, but it applies to the 737. And this says that on aircraft with AVM procedures, flight crews should also be aware that AVM indications are not valid at takeoff power settings, during power changes, or until after engine thermal stabilization. High AVM indications can also be observed during operations in icing conditions. So what all of this is saying is that there are a lot of caveats with the vibration. And really, I guess the bottom line to you as crew is that these are a diagnostic tool. There's something to have in the toolkit, but in and of themselves, they are not reason to shut down an engine. I mean, obviously over 4 units follow the procedure in the QRH, which has been improved significantly over the years. But really, as is good practice, always look for at least 2 parameters, engine parameters, before shutting down an engine. Vibration monitoring on the NG and the MAX is really quite a sophisticated business. This is the engine vibration signal conditioner unit in the eBay. That's actually only there on the NG. On the MAX, it's all actually done in the EC for what it's worth. But I show you this to kind of tell you that it's more than just some piezo electric meter pickup feeding straight to a gauge. It actually goes through this little computer. So the standard NG has got 2 vibration pickup points, one on the number 1 bearing inside the engine and the others on the fan frame compressor case. There's an optional advanced AVM which also monitors the number 3 and number 4 bearings. The number 4 bearing has been particularly problematic over the life of the CFM 56. The signals then sent to this conditioner, where they're processed, stored for diagnostics, and sent to the flight deck displays. So it's this bit about storing them for diagnostics, which is the extra bit that the NG and the MAX do. So the engineers use this stored data to calculate a balanced solution for engine vibration. And I mean, I've never seen it done, but I'm told that the old days of plotting out vibrations, and measuring fan blades and that kind of stuff are gone. This computer, this box, just tells you how to balance an engine. So it's great. It's definitely an improvement. I'll say the box isn't there on the MAX. It's all done within the EC. All right, on to reverse thrust now. The graphic at the bottom shows the original clamshell reverse thrusts. These were quite short-lived. They weren't very successful. These were actually pneumatically powered, which may come as a surprise to those of us flying the 737 today, where we're used to having hydraulically powered clamshell doors. But these were pneumatically powered from 13th stage bleed air, and these were straight off the 727. These things. So that bleed air rotated the deflectors and clamshells into position. Very ineffective, because what they did was they directed the exhaust vertically down against the runway, and that tended to lift the aircraft up when deployed, sort of hovercraft style, I guess, on this cushion of air. And that reduced the downforce on the main wheels, reducing the effectiveness of the wheel brakes. And again, I guess it was because these did come from the 727, where they were mounted significantly higher up on the fuselage, on the back of the fuselage, than they were on the 737. So anyway, these didn't last long, and they got quickly changed for target reverse thrusts very quickly. In fact, this is line number 135 onwards. So there are only 134 aircraft built with the clamshells. So these were changed by Boeing and Raw, and these were indeed hydraulically powered target type thrust reversers. They actually required a 48-inch extension to the tailpipe to accommodate the new deflector doors. These doors were set 35 degrees off from the vertical to avoid that cushion of air, that lifting cushion of air, the problem that was had with the clamshells. So that allowed the exhaust to be deflected inboard and over the wings and outboard under the wings, rather than towards the wheels and the wheel well or the engine exhaust. So again, there was less foreign object damage risk with this configuration. That new nacelle, as I said, was 48 inches or 1.14 meters longer, and that actually had a nice little side effect, because it improved the cruise performance by improving the internal airflow within the engine and reducing cruise drag. So it was a significant improvement. That's a close-up of these target thrust reversers. And they're locked against inadvertent deployment by both deflector door locks and the 4-bar linkage that you can see there being over-centered. And to illustrate how poor the original clamshell system was, Boeing's own data says the target type thrust reversers at 1.5 EPA, which is quite low, are twice as effective as clamshells at full thrust. And this is why you don't see any clamshells. Well, you don't see any targets these days. There are very few 200s flying, but they were all pretty much removed from service when the targets came along. On the CFM56, reverse thrust works completely differently. And I've got a couple of photos here showing a side-by-side of, well, the left photo is reverse thrust not deployed, and the right photograph is with reverse thrust deployed. Something we don't get to see really as pilots, but I very kindly got an engineer to take this photo for me, so you can see it. So when you select reverse thrust, hydraulic power pushes up these 5 blocker doors that you can see on this picture, but there are another 5 on the other side as well. So they go all the way around like sort of petals on a flower, if you like. They protrude into the bypass airflow. That stops the fan air taking its normal route around the core exhaust. This is just a close-up of the previous image, just to show you a little bit better the blocker doors. Now, at the same time, 2 translating sleeves. In plain English, it's the back half of the engine shroud moves backwards. Both the inboard and the outboard section. You can only see the outboard section on this photo, but on the inner side of the engine, that's moving backwards as well. And it's exposing these cascade vanes, which you can see now in view, and that allows that blocked bypass air to escape in a forwards direction, thereby slowing the aircraft down. The cascade vanes don't move, only the sleeves and the blocker doors move. Each thrust reverser can be deactivated by fitting 2 pins, one to each translating sleeve, and it connects the sleeve to the stable cascade support ring. The fitted pin will protrude for conspicuity, so you can see it during a walk around. And the photo below. Sorry, it's not a particularly wide shot, but that's what it looks like. So if you see that on a walk around, then you know. Obviously, it should be in the tech log as well, but it's another clue for you. Now, net reverse thrust is defined as the fan reverser air minus forward thrust from the engine core plus form drag from the blocker door. Now, as the form drag is significantly greater at high speed, reverse thrust should be used immediately after landing, or RTO if conditions allow, and should be reduced to idle by 60 knots to avoid engine ingestion damage. Um, it is possible to deploy reverse thrust when either radial is below 10 feet, but this isn't recommended. In the E&E bay is the engine accessory unit, and I've shown you the one on the left is that fitted to the Classics, and the one on the right is the one fitted to the NGs. Primary purpose of this is to control the reverse thrust stow operation. It's got a front panel bite test for troubleshooting. It uses 2 proximity sensors for each translating sleeve for control, and it interfaces with the thrust reverser indicating system to control the reverser light, which is that one that we see on the aft overhead panel. And this shows that either control valve or sleeve position is in disagreement, or that the auto restow circuit is activated. Now this light, it'll illuminate every time the reverser is commanded to stow, but extinguishes after the stow is completed. And it'll only bring up the master caution engine if a malfunction has occurred. Now, speaking from years of experience flying the 737, if you do get that happening, it's probably because the way, I say the way, the speed that you stowed the reverse, and perhaps you didn't stow it completely enough. A top tip, if you get this after you've vacated the runway or what have you, is just recycle the thrust reversers, and that will often, 9 times out of 10, clear the fault. If it doesn't clear the fault, then don't do it again. Just bring the aircraft back to stand and tell the engineers. If you get this light in flight, reverse thrust will be available to you after landing. The other reverser light, the more serious one, is the reverser unlock light, or REV on the NG and the MAX. And this is potentially much more serious, and this will only illuminate if a sleeve is mechanically unlocked. For this, follow the QRH drill, but we're told that only multiple failures will allow the engine to go into reverse thrust. If you get this, the EEC will prevent power above idle if the thrust reversers move from the stow position. So hopefully, if the multiple failures do happen, you should never get more than idle reverse thrust in flight. The original engine panel, this is on the 200s, was actually known as the thrust reverser panel, because that's all it did. Because of course there was no PMC or EC on the originals. First thing to notice at the top there is a low pressure light, and if you recall, I've said that's because the original clamshell reversers were pneumatically operated, and this was a warning to you that the reverser accumulator pressure will be insufficient to deploy the reversers. Moving down to the rest of the thrust reversers, you've got 2 red guarded normal override switches, and these are for engineers to select reverse on the ground with the engine stopped. The blue caption between the switches is actually says isolation valve, and that illuminates when the 3 conditions for reverse thrust are satisfied. So the engine's running, the aircraft's on the ground, and the fire switches are in the normal position. On the Classics, that same panel was redesigned quite significantly. Reverser light I've already spoken about, but we've got PMC lights now, as the PMCs were new to the Classic. PMC in op means it's in op, or it's been switched off, and the low idle light in between the 2 PMC switches means either that either engine M1's below 25%. The MEC is not commanding high idle when requesting flight, or that's an optional feature if the start switches are in flight and M1 below 45% M1. The low idle light's deactivated if an engine start levers are cut off. For the NGs, PMC was obviously relabeled EEC. And we've got alternate lights on there, which means it's if they illuminate, means it's automatically or manually switched to alternate mode. We got the earlier slide on that, and the engine control lights. These are the new ones to the NG. So the EEC has a non-dispatchable fault, and this should only come on the ground. It's inhibited above 80 knots. For the Max, the engine panel has changed yet again, and quite significantly actually. There's three new lights on here. The reverser command light warns the crew that the reverse thrust lever's not down in flight. That'll be inhibited on the ground. Reverser air ground illuminates when the air ground thrust reverser logic has failed. And reverser limited means there are faults being detected which will limit the reverse thrust on the indicated engine. If commanded, reverse thrust will either not deploy or be limited to idle. So think performance with that. Probably not best to go to a short runway if you've got those lights on. Engine ratings. Now, this slide is all about the classics. What the classics have in the E&E bay is an engine power configuration connector, which is this green plug that you see here. And this signals the maximum thrust allowable by the PMCs. And it's used by airlines to quickly and easy change the maximum selectable thrust rating of an aircraft, which they do to balance operational needs and maintenance costs. The plugs are color-coded by thrust rating to help identification. This is a green plug, so that's for 22k thrust, but you can switch that over to a yellow 20k plug if you wish to, and that brings down the maximum selectable thrust by the PMCs to 20k. And airlines would do that to reduce maintenance costs. But if they had a need to send an aircraft somewhere where full thrust, well, the full 22k was required, then they'd switch plugs again. I've only seen the green and yellow 22 and 20k plugs, but there are probably other ones available for 23k and 18.5k. But I don't know their colours, and I haven't seen them. The actual engine rating you can see on the FMC ident and the engine's ratings pages. So these are the 23.5k versions on a 737-400, and the lower screen is one that only the engineers would get to, although I've shown you how to get to it there from the INITRESH index maintenance or thrust by test engines and ratings, and that shows the thrust setting there. On the NG, different system. The identification plug as such, so the NG equivalent is that plug there that I've highlighted in the red oval, and this contains information about the actual engine type, so which particular 7B it is, M1 trim, which is a calibration of the M1 from your particular engine which has come out of the factory. It needs calibrating to the M1 demands of the EC. That's what M1 trim is. The thrust rating set for that engine, the engine, whether it's got the engine condition monitoring option fitted, and the combustor configuration, whether it's single or dual annular combustors. That data can be seen on the bite test and model engine config pages, which are given here, and you can see. I mean, these are just several that I've taken photographs of various aircraft I've flown over the years. So you can see the Series 600 there is the one with the dual annular combustors. Engine ratings there were 20 and 18k. The 700 again 20 and 18k. The 800s were up at 27k, and the winglet 800 had takeoff 1 and 2 modes optional available as well. The full list of engine types and ratings are in this table that I've compiled here. You can see which thrust rating you've got from your idem page. So the example I've shown here is of a Max 9 at 28k. That's the Max 9 can be fitted with either a 1B27, 28 or 28B1 engine. It could be any one of the three on here, because to find out that we'd need to go back to that engineering bite test page to see which was the actual model of engine. But the thrust rating, which is what you as the pilot need to know, is shown on your idem page here. The rest of the engine identification plug information can be seen on these pages on the CDU bite test, and I'll take you through these, because it's always interesting to know this stuff as a pilot. You know what's kind of behind the scenes. So this page is showing the engine and EC data. So the engine model there is a 7B20. We've seen from the previous table that the 7B20 can be operated at various thrust settings. So the thrust setting you'll see on your ident page, but the actual physical engine model is that one given there. You can see bumps not enabled. M1 trim I've already spoken about. It's the calibration of the particular engine with the EC. EC software part number and software version, whether the start mode is normal or enhanced, and the engine serial number is given there. If you go to page 2 of that, various other configs and options, it tells you whether they've been done or not. So PMUX is performance monitoring option. So it's otherwise known as condition monitoring. It tells you the sort of engine health, the how it's doing. DMS kit, whether that's been installed or not. This is debris monitoring system, which you may know as electronic chip detectors, or MCD, magnetic chips. So a magnetic chip detector, or debris monitoring system as it's called on here, if engine parts are deteriorating or rubbing together, it's possible that the tiny, almost microscopic little fragments of metal will come away, and they will flow away in the oil, hopefully. But that oil is monitored, is analysed real time with this with these chip detectors. And that's obviously flags up to engineering that, crikey, there's bits of metal chips in the oil from this engine. Take it off the wing, have a look at it. BSV is the burner staging valve. That's just a single annular combustion option, and where the ignition mode is standard or automatic. And I've mentioned the auto mode already, when that comes on with anti-ice. Following on from the bite test, the actual faults are shown there. So a couple of examples: the start lever signals disagree, and the airplane voltage input to the EC is out of range, and flight legs 0, 1, 2, 3, 0 being the current flight. Any with an X below it has got a recorded fault. And if you line select 6 right history, then you would actually get the data for legs 4 to 10 as well. This is an example bite test, so sort of taking you through the whole thing. This was an aircraft I was about to fly, and we got the EEC light on the aft overhead panel. So called the engineers, and they went in, did a bite test, and sure enough, what they found was an internal EEC fault. The message number, that's figure 73-10172, that's a decode for the engineers to go into the fault isolation manual. So 73 is the ATA chapter number, which 73 is engine fuel and control. The 1 means channel A, because remember the ECs have got 2 channels. 017 is the unique fault number, and the number 2 at the end means it's engine number 2. So there was with this there was fault number 017, whatever that is, to the EEC on engine number 2, channel A. And finally, this is a table I put together just listing all the various limitations and maximum and minimum parameters for the various engine series. Couple of limitations quoted there. Engine ignition must be on for takeoff, landing and operation in heavy rain and anti-ice. Intentional selection of reverse thrust in flight is prohibited. So those two are fairly obvious, I would hope. And the minimum oil starting temperature is -40. There you go. That is everything I know about engines on the 737. As always, if you've enjoyed this video, if you've found it useful, please give it a like and subscribe to my channel. It all helps with visibility on YouTube, helps spread the word and get it out there. Thank you very much.